Ever wondered how AI systems like GPT or BERT process language with such precision? The answer lies in a revolutionary architecture that's reshaped machine learning, the transformer. Today, we're diving deep into the technical heart of transformers, how they work, why they're so powerful, and the cutting-edge research pushing their limits. Let's get technical. Before transformers, recurrent neural networks (RNNs) and convolutional networks dominated NLP. But RNNs struggled with long-range dependencies, and convolutions lacked global context. Enter the 2017 paper Attention is All You Need, which introduced the transformer, a model built entirely on self-attention mechanisms. This shift eliminated sequential processing, allowing parallel computation and capturing relationships across entire sequences. The key innovation: the self-attention layer, which computes dynamic weights between every pair of tokens, enabling the model to focus on relevant parts of the input. Let's break down the math. For a sequence of tokens, the transformer generates three matrices: queries, keys, and values. The attention score between a query and key is calculated via a dot product, scaled by the square root of the key dimension, then passed through a softmax to produce weights. These weights are multiplied by the corresponding values, summing to a context-aware representation. This process happens in parallel across all tokens, making it vastly more efficient than RNNs. But here's the kicker: multi-head attention. By splitting the attention computation into multiple heads, the model captures diverse relationships, like syntax, semantics, and syntax-semantics interactions, simultaneously. Transformers don't have inherent sequence order, so positional encodings are added to token embeddings. These are fixed sine-cosine functions of position, allowing the model to infer relative positions. But scaling is where things get tricky. As models grow, parameters and data requirements explode. Recent research like the Scaling Laws paper shows that performance improves with more parameters and data, but efficiency drops. This has led to innovations like sparse attention, where only a subset of tokens attend to each other, and efficient attention mechanisms like longformer or linformer, which reduce quadratic complexity to linear. Transformers aren't just for text. Vision transformers, VTS, apply the same architecture to images by dividing them into patches, treating each as a token. This approach outperforms CNNs in some tasks by leveraging global attention. Meanwhile, research into hybrid models, combining transformers with CNNs or GANs, explores new frontiers. And let's not forget the rise of causal language models, which use autoregressive attention to generate text sequentially, powering applications like code generation and dialogue systems. Despite their success, transformers face challenges. Their computational cost remains high, and they struggle with tasks requiring reasoning or external knowledge. Researchers are tackling this with techniques like knowledge distillation, where smaller models mimic larger ones, and neural-symbolic integration, blending symbolic logic with neural networks. The future: models that balance efficiency with capability, perhaps through architecture innovations like the efficient transformer or research into quantum-inspired attention mechanisms. Transformers have redefined what's possible in AI, but the journey's far from over. From self-attention to vision applications, their impact is everywhere. For those diving into AI research, understanding their inner workings isn't just academic, it's essential. Stay curious, keep exploring, and remember, the next breakthrough could be just a few equations away. Thanks for watching. If you want to dive deeper into transformer architectures or specific papers, check the description. Subscribe for more technical deep dives, and hit that bell so you never miss an update. Until next time, keep learning.